Hello, my name is Scott Sheeter. I'm a principal engineer at Slipstream. The topic of this video is occupancy and vacancy lighting controls, a control strategy that automatically reduces or turns off lighting when a space is vacant or not occupied. This video is part of the ESTCP Advanced Lighting Controls Technology Transfer video series. I'll begin by describing occupancy and vacancy controls and why we care about them, followed by some discussion on selecting the right technology and advanced control strategies that optimize system performance. I'll also review the energy savings potential of these kinds of controls and wrap up with some discussion on design best practices. Most of you likely recognize each of these lamps or light bulbs. On the far left, we have the incandescent lamp, which was used in buildings beginning in the early 1900s and produces more heat than visible light. Technology advancements brought about the fluorescent lamp, which was a substantial efficiency improvement at the time. Today, LED is the lighting product that dominates the new and replacement lighting market, and it's easy to see why. Each of these lamps generates a similar amount of light or lumens, but we spend 100 watts to generate that light with an incandescent lamp, 27 watts with a fluorescent, and only 16 watts with the LED lamp. With all that background, let me pose this question. What is efficient lighting? In the simplest terms, it's doing more with less. Now, choosing an efficient technology is certainly important, but the most efficient fixture is going to be the one that is off when it is not needed. Fortunately, we have several automatic lighting control solutions to help us with this in commercial buildings, which is where occupancy and vacancy controls come into the picture. Occupancy sensors are not a one-device-fits-all applications kind of technology. Some devices use passive infrared sensing technology to detect the movement of heat. Passive infrared is the most common technology. Other devices use ultrasonic sensing technology to detect changes in reflected sound waves outside of our range of hearing. Microphonic sensing technology detects sounds indicative of human occupancy. Dual technology devices combine more than one technology into a single device, which is typically passive infrared and either ultrasonic or microphonic. Lighting practitioners are knowledgeable on how best to apply the various sensing technologies. For instance, a technology that does not rely on direct line of sight, like ultrasonic, is essential for proper function in spaces with tall partitions, like toilet rooms or open offices. Ultrasonic, on the other hand, can be problematic in places where higher HVAC airflows are likely to trigger false occupancy, keeping lights on when a space is actually vacant. Let's start by clarifying the difference between occupancy and vacancy controls. Both strategies reduce or turn off lighting when a space becomes unoccupied. Where they differ is their on control. Vacancy controls require that lights be manually turned on, typically by the press of a low-voltage push button like shown here on the far right. Occupancy controls automatically turn lights on, typically either to 50% or full brightness. Coverage patterns for various sensing devices differ as well, with some better suited to long, narrow spaces like hallways or various warehouse aisles. Others, like the passive infrared sensor shown here, have major motion and minor motion coverage patterns that are circular in shape for placement on a ceiling or pie-shaped to accommodate placement of a sensor in the corner of a room. Movement across the sensing rays is required to detect occupancy. Poor sensor placement could allow a sensor to see occupancy in an adjacent space, keeping lights on that could otherwise be off. Too often, the design of the lighting controls is an afterthought or left up to a contractor to determine at the time of install, particularly in retrofit applications. However, with all these design elements involved, it's easy to see why a lighting practitioner should be involved in the process. Sales reps or manufacturers frequently offer design services for both lighting controls at no cost, but this service must be requested prior to system installation. Other aspects that a lighting practitioner will consider are sensitivity settings and time to light off. A lower sensitivity may be necessary for a device located near a doorway, while higher sensitivity might be necessary to help a sensor more quickly see when someone enters a room. A short time delay can increase energy savings, but when that is too short, could inadvertently turn off lights before a space is actually vacant. Proper implementation of control strategies and control device settings is critical to ensuring savings persistence, as occupant complaints can drive facility maintenance staff to simply disable lighting controls when not operating as expected. We are beginning to see installation of a new market-ready technology, luminaire level lighting controls, which integrates sensors into each fixture. Not only can we automatically turn off lights in spaces when they are unoccupied, but the granular sensing array inherent in having a sensor in each fixture allows us to do this with confidence in much less time following actual vacancy. This approach, in its simplest wireless form, simplifies lighting control system programming, making it more likely to work as intended and therefore delivering the expected energy savings. Beyond the capability to yield even higher energy savings than traditional lighting controls, luminaire level lighting controls also have the potential to reduce first cost by removing the need for control wiring, a considerable labor savings in a retrofit application. A wireless solution also makes the controls more easily reconfigured in response to changing needs within the workspace. In thinking about this from the perspective of an opportunity for a deep energy retrofit, you should take full advantage of a lighting control system's capabilities. For example, what is depicted here is a lunchroom that strategically applies both occupancy and vacancy control. Occupancy controls are programmed with a 5-minute or less time delay along the counter, while people frequently stop at the coffee maker, sink, or refrigerator. Vacancy controls that require a manual on are applied in the seating area to the right, keeping lights off until that portion of the space will actually be occupied. So, when someone comes into the lunchroom to get a cup of coffee from the counter and then leave, only the lights nearest the counter will automatically turn on. If that same person wants to sit and enjoy their coffee, they would manually turn on the associated lights with this area. Overall, this strategy saves energy compared to occupancy controls only or no lighting controls at all. In this example, two strategies are depicted. Smaller zones coupled with the strategic blending of occupancy and vacancy controls to keep lights off in those smaller zones when unoccupied. A more traditional approach would be a single zone with basic occupancy controls that would keep lights on throughout the open office if any portion of the space was occupied. This all circles back to the concept that the most efficient fixture is one that is off. So, while it is commonplace to create a drawing to document a light fixture layout, documentation of lighting control design intent is seldom required. A control matrix or schedule of some kind, which details the lighting control design intent, can be easily incorporated into design documents and ensures that a contractor has a clearly defined scope. This is a critical step necessary to realizing and maintaining long-term what is significant potential for lighting control energy savings. A clear scope of work can also be beneficial in avoiding inflated project costs during project bidding. A facility manager should make it standard practice to request this type of documentation for every lighting project. Important elements that need to be captured when implementing occupant controls, and shown here in bold text, are the control mode and the time delay to off. These parameters should be programmed immediately following fixture installation. Also, providing occupants with information explaining the basic and expected functionality of their new lighting and controls can help achieve improved overall occupant satisfaction. Perhaps you're wondering just what kind of savings you can expect to realize with occupancy controls. Let's explore that question by first reviewing this plot of an existing lighting system's power over a typical day, shown here in blue. Note that this system does not have occupancy controls. In the morning, the lights come on to their full power and remain there throughout the day, before being shut off at night, when the system is retrofit to incorporate occupancy controls. The lights still come on to full in the morning. However, as the business of the day gets underway and occupants move about, attending meetings or stepping out of the office for a noon break, lights in unoccupied areas turn off. This reduces the lighting power of the lighting system. The green shaded area of the plot represents the energy savings that result from occupancy controls. According to a meta-analysis conducted by Lawrence Berkeley National Lab and published by the Illuminating Engineering Society in 2012, The average lighting energy savings potential for occupancy controls is 24%. That savings potential can vary depending on the type of building or the types of spaces that make up a building. Spaces with more variable occupancy, like a conference room or lunchroom, will yield higher savings, and those with less variable occupancy, like an open office, will have lower savings. Energy codes and UFCs address this significant savings potential by requiring occupancy controls in those space types with more variable occupancy. In the two previous videos, we discussed advanced lighting control strategies called task tuning and daylighting. You might wonder how these three lighting control strategies interact when combined. This plot illustrates the combined energy savings over an ideal day. Task tuning savings are indicated by blue shading. Automatic daylighting control savings are indicated by orange shading, and occupancy control savings are indicated by green shading. The solid red line plots the lighting power system over a typical day when all three control strategies have been implemented. This brings us to the conclusion of this video. More information on this topic is available on several websites listed. The Designs Lights Consortium also maintains a qualified product list of network lighting controls that include occupancy controls. Thank you for watching.